So for problem A1 of the homework assignment, I solved in Python, and I started by importing NumPy, um, matplotlib.pyplot, and pandas, in case I needed any of them, which I didn't end up using pandas. But I initialized my variables. I had an alpha converted just to decimal, or and then I had my stability criteria of point 0 of point 0.5 so that I can cancel out that entire right side of the equation, like it said on the homework, or thickness of point 0.05, and then I used these. I showed that the entire wall would be 300, so I put initial and our left. These could have been either side, but I just did left and right. But I didn't use these three. My x would start at 1. My uh, change in x would be 1 per step. My t would start at 1, and change in t would be 1 per step. And then I just initialize these variables as well at 0. This is later on for interpolating, and initialize these variables as well. And I started off by creating an array of 21 across, going from the left part of the wall to the right part of the wall, and like 10 would be the middle. And that was my goal for the array. And I just made a bunch of zeros at first because I don't know too much about Python, but I made it a bunch of zeros, and then thought I would edit those zeros. So I took the entire array and added 300. So it said everything will be at 300 instead of everything being at 0. And then I took just the entire left column and I turned it to 425 by adding this to that left column. And then I took the entire right column on the right, which is the right side of the wall, and I made that equal to 600. And then yeah, so the center of the wall is at this point of colon comma 10 in the that would be the entire middle column. And then this is kind of how I did it. So went from T and X, where my indexes for my 2D Python array that I created. I initialized, and then the first thing I needed to find was where the T center of the wall, the temperature of the center of the wall equals 425 for the first time. And in order to do that, I created a loop inside of a loop. So the first loop that I had here went so it went from X from 1 to 20, because you don't want to include the one on the left because you don't want the left part to change. You don't want your 425 to change. You don't want your 600 to change. So I did 1 to 20. And if x equaled 20, then break because you don't want it to run for that. So that loop would end at that point. But basically, it would calculate using um, like the position of the array would be here. You'd have your value, and then um, for your t, you get by going back 1t. So it would take you up 1, and then back 1x, so minus 1, and you'd get, so you go up and left 1, you'd use that like cell of the array, and then up 1, right 1, that cell of the array here, and you add those together and divide or multiply by the stability criteria, which is 1/2. And then it kept running that for all like 20 of those, except excluding the left and the right, and it basically did it for the entire row. Then when that broke, it would go through this, which set x back to 1 to reinitialize this, and it went and basically ran this loop for every t value all the way from 1 to the end. And you don't keep that first row. You want to keep that first row initialized due to the fact of that you use those for calculations, and those don't change. They're just the initial at t equals 0. Um, but yeah, that's how I found my critical. And oh yeah, so once it got to the point, once this ran and finished, if the data for that t at 10 was more than 425, I told it to break, and I took the t value, which represented the number of time intervals of the upper and the lower at that T for interpolation later. But and then um, I just redid these two loops without breaking at this point for the interpolation values, just so I had the full array from like for 394 T values basically. Um, and I that just got the entire range again. And then so then this is whenever I was trying to interpolate later. So I found the T of the lowercase t value, or the time intervals at the lower part of that interpolation. The temperature there is found through this. The temperature of the upper is found through this, and then I interpolated using the uh, both of those to find your number of t. This would be your t, your number of time increments whenever the uh, value of the middle of the wall is equal to 425 degrees. And then I determined your delta t, which is the amount of time in hours for one time interval of t. And you did that by doing the thickness divided by 20, which is our total divisions of the wall, and then to the power of 2 times the or over um times the stability criteria over a, and then I converted from seconds to hours using this 3600. So that would give me my delta t, and to get the total time, you do the delta t, which is how much time is in hours for one time interval of lowercase t, times the amount of time intervals it took. And that's how I got it, and then I just rounded it, and that ended up being 17 hours. And then for the graph, I mean that's pretty self-explanatory. I just went from 1 to 396 in increments of 1, and the x-axis was, and I multiplied it by the delta t as well. And then the y value is the temperature of the middle for all those x values, which were basically the t's in hours, like the number of time intervals in hours. And then for my problem that I selected, the aluminum plate of, I mean, you can read this yourself, but basically, we had to determine the thermal contact conductance of the aluminum copper interface here. Um, and we're given some different values. We're given thickness, um, convection heat transfer coefficient, heat flux, some different values we were given here. The and then what I did to calculate this was you set up this resistance thing, and you get the R total is equal to the R of the interface over A plus the R of the plate plus R of the um, ambient or the air. And I wrote out how you do this here. Um, and then you solve for the R total. Um, and then so you have this expression for that. And then what you do at that point is you get this the heat flux times the area is equal to the delta T over the R total, and then you relate those two expressions together. So you get this expression from this T1 minus T infinity over the heat flux times the area, and then you relate this with this expression. You put them equal to one another because they're both equal to R total, and then at that point you would solve for the R interface. That's what we want. We want the R interface, which will then give us our thermal contact conductance, as it says here, thermal conductance of the interface. Um, and so we do that by taking our T1 minus our T infinity over the heat flux, which the A's canceled up here, as you can see, and then minus your thickness over um, your K value minus 1 over your H of infinity. And you end up getting your R interface value. Then, to find the thermal conductance, it's very easy. All you do is 1 over the resistance of the interface, which gives you this. And then, once I'd solved it by hand, I went and solved it in Python. So I imported these as before, put what the aluminum plate thickness in millimeters, copper plate thickness in millimeters, our K value, uh, our convection heat transfer coefficient, and our T1 and T infinity. And then at that point, once I initialized those values, it was pretty self-explanatory compared to the other problem, where I used the thickness. I converted both thicknesses to meters, and then I did the resistance of the interface equal to that same formula shown before, just in Python, and then I printed it. Thermal resistance of the interface is 6.23 meters squared Celsius per watts. And then to calculate thermal contact conductance of the aluminum copper interface, you do 1 over that, but since we want it in kilowatts instead of watts, we divided by 1,000 and got 15.98 kilowatts per meter squared Kelvin. And that's about it. And that was major assignment A1 and A2 by Trey Smith. Thank you very much.